Okay. We are going to look at determining the number of terms in a geometric series. So the sum of n terms of a series, that is 5 plus 15 plus 45, is 16,400. Determine the number of terms by solving an equation with a common base or by using the intersection feature of a graphing calculator. So if we use a common base, we have our formula S of n equals a times r to the power of n minus 1, and then divided by r minus 1. So S of n equals 16,400. A equals 5. And what's my common ratio? 3. So I have 3 to the power of n minus 1 divided by r minus 1, which is 3 minus 1. So 3 minus 1 is 2. And then I'm going to take that 2 and multiply each side by 2, because this is a dividing by 2. So if I multiply my 16,400, I will get 32,800 equals 5 times 3 to the power of n minus 1. And what I'm trying to do is I'm trying to eventually get this 3 to the power of n by itself. So divide by 5. And when I divide by 5, I get 6,560 equals 3 to the power of n minus 1. Add 1 to each side. And I get 6,561. Now what I want to do is I want to figure out 6,561 can be written as 3 to the power of what? So I have to guess and check it. I don't know, start off with 3 to the power of 6. Not big enough. 3 to the power of 9. Too big. So now it's somewhere between 6 and 9. It's not 7. 3 to the power of 8. So I get 3 to the power of 8 equals 3 to the power of n. And from there, if these are equal, it implies that n has to be equal to 8. So there are 8 terms. If I was to use a graphing calculator, I could let y1 be equal to this 16,400, and then let y2 be equal to 5 times 3 to the power of n minus 1 over 2. That's the 3 minus 1. So this one's takes a little bit of maneuvering because of my window settings. So I've got 16,400, and then to put this into my calculator, bracket, 5 bracket, 3 to the power of x minus 1, and then I would close the bracket twice, and then divide it by 2. Now when I have to go and adjust my window settings, because my y1 is equal to 16,400, I need to make sure that I go up to that height in my y's. So my y's can start at 0 and go up to like 20,000. My scale could be every 5,000. And then my x's, well, I know that it has to be more than 0 terms. It can't be negative terms. And then I could leave it at 10 and just see what happens. If I can see an intersection point, I'm good. If I can't, then I might have to make an adjustment. So if I press the graph button, there's my y1, and there comes my y2. And now I can use the intersection feature, second calc, 5, scroll over on this line as close or closer to that intersection, and there's my 8. So if you were using the intersection feature of a calculator and you were showing this to me, what I would expect to see is your Y1 and your Y2s, and I would expect to see your window settings, so that I could recreate this. And if I recreate this, I should be able to see the intersection. And then x equals 8. So again, 8 terms. Okay. Class example number 7 becomes an application question. Where could I possibly use the concept of a geometric series? So if I drop a golf ball from the top of the building that's 100 meters above a paved road, in each bounce, the ball is going to reach a vertical height that is 3/4 of the previous vertical height. Determine the vertical height after the 7th bounce and the total vertical distance when it contacts the floor for the 7th time. So, what should A or T of 1 equal? What would my first term represent? The height after what? Okay, the height after the first bounce. So what would be the height after the first bounce? $75 meters. 100 meters times 3/4. So that would be the height after the first bounce. So then T of 7 becomes the height after the 7th bounce. So 75 is my first bounce. 3/4 is my common ratio. Tell me what the height would be to the nearest 1/10 of a meter. What'd you get, Rachel? 13. Okay. B says calculate the total vertical distance traveled by the ball when it contacts the floor for the 7th time. So it might be useful to sketch what this is going to look like. And I'm going to sketch it up here because I have room. There's my building. And there's the ground. So the ball gets dropped off the building. This is the first bounce. Goes up to 3/4 of the height. Second bounce. Third bounce. Fourth. Fifth. 4, 5, 6, and there's where it reaches the 7th bounce. So in the question that we just did, we actually found this measurement right here. This was the height after the 7th bounce. For part B, we're trying to find out the total distance when it contacts the floor for the 7th time. That's to here. So I want to know what this height plus 2 of these, plus 2 of those, etc., etc. So what I'm actually calculating, the sum, is going to be 100 meters plus 2 of the T of 1s plus 2 of the T2s plus 2 of the T all the way up to 6. Because this is the height after the 6th bounce. I don't want T of 7 in there because T of 7 was my height after the 7th bounce. So this becomes 100 plus 2 of my sums of 6, 2 of my S6s. T1 plus T2 plus T3 plus T4, all the way up to T6. So let's figure out what S of 6 is. If I use my formula, A times R to the power of n minus 1 divided by R minus 1. So in this case, I don't know, it might be easier instead of using A if we actually use T of 1. Because T of 1 represents the height after the first bounce. So the height after the first bounce is 75. R is 3/4. So when you go to put this into your calculator, you may want to put this in stages. So you might want to start off with 3/4 to the power of 6. And then minus 1. And then multiply that by 75. And then my last step would be to divide that, and I would put this in one step. My 3/4, I'm going to write it as 0.75 because it's easier to put into my calculator than putting 3/4 is. This is going to give me a negative 0.25, so my answer should still end up being positive. So 246.6. That's the sum of the 6 bounces, and that's either the 6 bounces going up or the 6 bounces going down. To calculate the total height, I need to double that number and then add it to 100. And I should get 593.2 meters.